Shall I start?
Yeah, yes, Deepa, please start.
Okay. Hi, good evening all. Again, I'm Deepa here, Academic Counselor of MyQT. Here we are with our next section, Physics for Quantum Computing. So, your valuable cooperation and feedback are greatly appreciated as they contribute to the continuous improvement of our upcoming sections. And a few words about MyQT. MyQT technology is your partner in quantum computing journey, providing innovative quantum computing training and solutions. MyQT is a repository of world-class knowledge and wisdom contributed by the best minds in the field of quantum computing. MyQT operates across the globe through its vast network of affiliates and partner organizations. MyQT provides a wide range of offerings including training, certification courses, research opportunity, and consulting services. Now, it's a great pride to introduce KG here. Welcome, KG. KG, that is Karthiganesh Durai, is a software engineer turned into data scientist who working on building quantum machine learning solutions. KG has master in computer applications from NIELIT and masters of business administration from Pondicherry University. Currently, KG is working as chief quantum architect in Boson Cube PSI PVT Limited. He is the co-founder of Quantum Computing India in November 2019. KG worked in Dell Technologies Bengaluru, Synergy Consultants, Singapore, Keppel Shipyard, Singapore, and Alam International, Singapore. Now it's time to start our section. So I hand over to KG to continue the section. Thank you.
Thanks, Deepa. It's a great pleasure again to meet all the quantum enthusiastic and the professionals on the another introduction level session on physics. Usually last session we had mathematics for quantum computing. This time we are going to discuss physics for quantum computing. Hope my presentation is visible now in the presentation mode.
Yes, KG.
Okay, right. Cool. So let us continue. So today agenda includes architecture of quantum computer, then types of quantum computers, and the qubits, how qubits working, and what are the different ways to build for qubits, and timeline of quantum computers. Then we are allocating more time for questions and answers. So this session is planned for people who are interested to know how quantum computer is working. So in the process, we will cover this agenda. So if any of you have any other questions, you are struggling to find answers, feel free to ask the question in this forum because we have sufficient time to answer most of the questions. Okay. With this introduction, let me start the architecture of a quantum computer. So this particular architecture is specific to superconducting quantum computers, but there are many other quantum computers that which we are going to see in upcoming session slides. To start with, this is a typical block diagram of a quantum computer, and you can see here this is the quantum processor. Let me highlight with the, let me take the laser pointer. So this, what you are seeing here is the quantum processor, and this quantum processor is at the bottom of the chandelier approach or chandelier structure. This quantum compute processor needs very low temperature, which is cooler than the outer space, minus 273 degrees Celsius. Imagine that. It is really very difficult to generate or to reduce the temperature to that level, which is cooler than space. That is the reason why we are using refrigeration unit powered by cryogenic engines. Recall that the cryogenic engines are powering rockets. That level of powerful cooling system is required for operating quantum computers. That is the one of the biggest engineering challenge and cost factor of quantum computers. You may recall that one quantum computer will cost 10 million to 50 million to build. The major cost portion is one of the reason for this cryogenic engine for this refrigeration units. Here, this quantum processor can process only quantum information, not classical information. So what is quantum information and what is classical information? We know classical information, nothing but binary data. See here, this binary data, 0 or 1. 0 or 1 are binary data. But as you know, the quantum computers can be in 0-ket, 1-ket, and superposition. Considering this superposition, it is being represented using the properties of particles, fundamental particles like electron, photon. So what are the fundamental particle properties like phase, then uh, amplitude or intrinsic angular moment? Those kind of properties are being processed by quantum processor. So here the binary data need to be encoded into quantum information such that it is being processed. So for encoding, it is not translating, it is called encoding. That encoding pass through, actually this is the unit which is encoding your classical data into quantum information. So that conversion of classical data encoding is enabled by this qubit signal amplifier, superconducting amplifier. Then since when you are translating or encoding your classical data into particle properties, you need to shield the anyone others can mute the mic. Okay, right, cool. So the inference, or it should be shielded against electromagnetic or any other radiation. Electromagnetic shielding, radiation shielding, because the quantum computer properties, particle properties are fragile. That's the reason why we need this kind of bulky architecture for creating or building the quantum computers. After the information is processed inside the quantum processor, that will be transmitted back. So now the quantum information must be encoded into classical data. That's where this process will, um, the qubit amplifier, whatever we are here. See here, actually this qubit amplifier, here is one conversion, then here is another conversion. It is not encoding decoding, it is both are encoding only. So this classical data is encoded, sorry, not this one, this one. This is encoded. After processing, this quantum information encoded into classical, then transmitted back to the classical data storage. So now this portion is connected to our cloud. You might hear that IBM, AWS, Google, Xanadu, all these organizations are allowing us to connect to their quantum computer. And our data is classical data. Now, this is the way. Here, there will be a cloud. This classical data, this data center is connected to cloud. That is how we are accessing. Is it clear? The components of quantum computers. Anyone, if you have any question, feel free to ask me. I can answer, because this understanding this portion is very, very important. So here you can see here from 27 degrees Celsius, it is getting reduced to minus 273 degrees Celsius. You can remember 27 degrees Celsius. It is always easy to remember. 27 is the normal temperature. Put a zero next to that one, put a minus. That is where your quantum processor is operating. Human cannot survive that. So this is very easy to understand, this architecture. And as I told you, This is superconducting quantum computers. Okay. Can I move? Can I proceed to next slide? Any question here? Please raise your hand or ask the question in the chat window. There is some chat window. Let me check. Is there anyone? Okay. Deepa, please watch chat window. If there is any chat window, stop me. I will explain that question. Okay. Right. Cool.
Okay, teacher.
Let us move on to next slide. See, when you are understanding the quantum computer, it is necessary to compare this architecture of quantum computers with the classical computer. Why it is necessary? Because we can easily compare how complex is the quantum computer. So I believe that most of us know these are the components in the classical systems. There is either desktop or laptop. You have all the devices like drive, power connector, SLPS, um, motherboard, then fan, cooling fan, then RAM, all those things. Inside the motherboard, we have microprocessor, which is the digital electronics based device, which is processing the binary data. If you take the microprocessor, inside the microprocessor, you can see um, control unit, ALU registers. This portion is the component of the microprocessor. And this microprocessor is connected to RAM memory, hard disk. Main memory is nothing but RAM. Secondary memory is the hard disk. It is connected to this one. Then the external device is connected. So inside the microprocessor, you have control unit, ALU, and register. Now you try to enter into this ALU. Now I want inside the ALU. If you go inside the ALU, you can see a register or circuit called full adder. Let me write it here. So inside that, you will see full adder. If you are from electronics background, you can connect easily. You can understand these things. So a full adder is circuit which is performing addition, because that's why it's called full adder. Am I right? The name itself tells it is a full adder. If there are 8 full adder arranged in a cascaded manner, that is a 8-bit microprocessor. If there are 62 full adders, that is a 62-bit microprocessor. It is easy to understand. The number of full adders gives you the bit. You might have seen 32-bit, 64-bit microprocessor. That is based on the number of full adder. So this full adder is performing addition, subtraction, multiplication, division, and other arithmetic operations. Now you may have a question. Addition, repeated addition, multiplication, we can understand. So a full adder is enough to perform multiplication. But how a full adder is performing subtraction? Anyone know answer for this one? You can raise your hand. How a full adder is performing the subtraction? Any question? Anyone knows? Please raise your hand. Someone is typing. Let us wait for the answer. Because if you understand this one, you will really start appreciating the mathematics. That's the reason I'm asking this question. Someone typed the question answer or something. Anyone from digital electronics background?
Sir, like we have
Yeah.
like concept of carry, like we
Yeah, that answer is correct, but you missed one technical term, important technical term. Carry is correct, but
yeah,
carry
memory,
of
like
2's complement.
yes, right, yes, correct.
Yeah, it is.
Carry of uh, it's one's complement, right?
No. It is 2's complement. Once it will create 1's complement, then increment it to make 2's complement. The reason
Yeah,
is that
correct, right, yeah,
if you
plus one,
add
right.
with 1's complement, you can't. The subtraction will give one answer. That is the reason why it's always radix complement. 10's complement, 2's complement, 16 complement, 8's complement. But in binary, Directly doing 2's complement is difficult, but 1's complement easy, because 1's complement just negate all the bits. That will become 1's complement. Then increment it. It will become 2's complement. So there will be two full adder, two full adder circuits. Register A, see, full adder is accumulator. Then register B, it is just transistors only. Register full adder will have first number. Transistor will have the second number. The transistor can be negated, meaning that ones can become zero, zeros become one, which is 1's complement. Then it will be incremented to become a 2's complement. Then this number get added. When you add one number with its 2's complement, the result will be the subtraction. You may not believe it. Let me demonstrate it. See, imagine that I want to subtract 8 minus 2. Okay. Instead of 2's complement, here am I going to show 10's complement. So 8 plus 2's complement, sorry, 10's complement of 2 is 8. So 8 plus 8 equal to 16. Am I right? Now ignore the carry. What answer you got? You got number 6, right? What is 8 minus 2? You got the result, correct? This is how a full adder is able to perform subtraction. That is how a digital computer is built. This is a concept from Boolean algebra because of the 2's complement. But complement is a general mathematical concept. Radix complement is a general mathematical concept which allows you to perform subtraction in the form of addition. Like this, there are multiple operations available in digital computer. But if you go back to quantum computer is not used for just addition, subtraction, like these kind of operation. Quantum computers are meant for problems like which are classified as NP problems and NP hard problems. I'm not going to explain now because we have another session for these things later. But why I'm explaining this one, after hearing my example of full adder in digital computers, you may think that is this something like that complements used in quantum computer? No, we are not using complements in quantum computers. The reason is that quantum computers are operating on complex numbers, whereas digital computers are operating on binary numbers. So the formula or mathematical model meant for digital computer will not work in quantum computers. Here we have entirely different mathematical model. That's what we discussed in previous session. Okay, so with this I'm stopping here, but I believe that the comparison of quantum computer and digital computer helps you to recall certain aspects. So when we are able to perform all complex mathematical operation just with the binary Boolean algebra and binary numbers, and think about the capability provided by quantum computer, which is operating on linear algebra and complex number. It is much powerful. Those powerful are defined by these keywords. If your problem is NP hard or NP, you will use quantum computer. I will give you one simple example. You know the game tic-tac-toe. So something like that's a 3 like this. Remember this game? This game is a P problem, polynomial time problem. But a chessboard is NP hard problem. Now you will be able to understand what is a P problem, what is NP problem. So P problems classical computers can solve. NP and NP hard problem, quantum computer will solve. Is it clear? With this comparison, let me move on to the other next slide. I'm ready to. Is there any question for anyone? Feel free to raise your question. Raise your hand if you have any question. Sorry. Please raise your hand if you have any question. I got confused. No question? All clear? Great. Now let us move on to the third slide, which is discussing different types of quantum processor. Sorry, I feel like sneezing. So what we have discussed now is called superconducting quantum processor. Superconducting quantum processor is again another physics problem. We are not going deeper into this, how these things working now. But if time permits, if you have questions, we can discuss that also. But I'm not planned for today because that will be overwhelming. There will be more information. I don't want to overload you with a lot of information. So that is the reason I just I'm covering. IBM, Google, Rigetti, these organizations are building quantum processors based on the superconducting. See, IBM is having IBM Q, then Google have Sycamore, Rigetti, Aspen, M. These are all superconducting. Trapped ion Q, there is a company called Ion Q, Honeywell. These are all trapped ion based supercomputers. Photonics actually optical based photonic quantum computing. Xanadu, this is this. See, this is Xanadu. This is called Borealis. This Borealis is the photonics based thing. The neutral atom, actually these two things are IonQ and Honeywell. And neutral atom, I don't have the image here. AQT, a company called Alpine Quantum Technology. They are building quantum computers using neutral atom. And apart from this quantum computing, there is one more technique called quantum annealing. The quantum annealing is a kind of special problems. D-Wave is building quantum annealer, and that is giving 2000, 4000 qubits. Whereas IBM and Google Rigetti, they are struggling to build 79 qubit. Recently, IBM released 433 qubit. If you are regularly watching the news, you may know that IBM released 433 qubit quantum computer. But using annealing, they are D-Wave or manufacturing or assembling 4000 qubit annealers. But their mathematical model is something different. That's the reason why they are, even though they are qubit, they have fabricating more qubits. It is not giving the computing advantage as per the quantum computing. Any question? Okay, no more question. Cool. So considering these various types of quantum processors, now you may be interested to know what are the various companies or different types of quantum processor. I'm going to share one link with you in your chat window. I believe all of you are able to access chat window. In this Wikipedia page, you can see different types of quantum processors. And there are different companies like IBM, Alpine Quantum Technology, Atom Technology, Google, IBM, Intel, IQM, Oxford, QTech. These are all various, the Quantinium. There is one company called Quantinium who are building trapped ion systems. And these systems are available in Amazon AWS Bracket. There is a platform called AWS Bracket. AWS Bracket is offering access to quantum processing in QPUs from IonQ, Rigetti, OQC, and Xanadu Borealis. Now, last 2 weeks it's not available, but earlier it was available. Prior to that one, till February, they were allowing D-Wave annealer also. AWS is offering that one. And all other organizations are offering their quantum computing through cloud. For example, if you want to connect to D-Wave, we can talk to D-Wave and then get access to this one. All are costly, but for research purpose, that will work. Corporates are spending a lot of money on those services and then trying to build solutions based on quantum algorithms. So that is where the need for quantum algorithms are increasing. There are many universities offering quantum algorithms. Even IISc Bangalore, they are offering PhD in quantum algorithm. So the demand is increasing. That algorithm is depending on the various technology. Why I mean the algorithm? Before you are building a quantum solution, you should identify what is the underlying technology for the quantum processor. Because superconducting is different, trapped ion is, see, they have certain operation is common, but they have some special operations also. Trapped ion will have some special operations. That is why this session, this physics session, will help you to understand what are the different types of quantum processor available. That is the first point, to know that we have superconducting, trapped ion, photonics, neutral atom, annealing. These are the different types of quantum processor. If you know that, then only you will be able to deep dive. Hope you understand why we are discussing this quantum processor here. Any question so far? All good? Okay, right. Can we move to next slide? Now we are going to discuss the fundamental part. Like in classical systems, we have bit, right? A binary digit, which is 1 or 0. That is what bit. But in quantum computing, the fundamental element is qubit. A qubit will be in 0 ket. They mentioned that as a 0 ket. It is not called a 0 bit, it is called a 0 ket. Then it can be in 1 ket, and it can be in a superposition, which is called psi-ket. Mathematically, we are representing as a psi-ket, which is physical phenomena. It is called superposition. So that's what I put it here. Up, the spin of electron, it can be up, down, or superposition, meaning that in between up and down. Similarly, the polarity of a photon can be horizontal or vertical, or in between horizontal vertical, 0 degree, 90 degree, or else in between 45 or 38, that is superposition. So any system or any particle in this subatomic scale, whatever I'm referring now, these are all subatomic scale. Please remember that the keyword is subatomic scale. The word subatomic scale indicates that we are going into particle level, like electron, proton, neutron, something like that. We are going into that level and manipulating those properties of those fundamental particles. Now you will imagine how deeper we are going into the atomic scale, subatomic scale. That's those things are called quantum realm. Or it is a movie term, but we are going into subatomic scale. If you have watched the movie Ant-Man or the Avenger Endgame, you can recall that they are going into quantum realm, right? So, which means they are going inside subatomic scale, inside the electron, inside the photon, something like that. That's what that movie story. Though those things are fictional, but they will help you to understand some of the physics also. That is the reason I recall that movie. Anyone want to share any point here about because the technology is okay, but the Ant-Man movie or the Avenger Endgame, And then there is another movie, Transcendence. These are all movies dealing are fictional movies using quantum technology. There will be some reference about the quantum technology in those movies. Sometime back, out of interest, I searched for Hollywood movies um, with the quantum technology discussing or based on quantum technology. You will find a lot of movies, and if you are able to try to watch them, those are fictional, but that fictional concepts helps a lot to understand. Okay, now this qubit, it can be in 0-ket, 1-ket, or superposition. So to visualize this and then represent mathematically, we are using a tool called Bloch sphere. This is the sphere space. So sphere means 3D, right? 3D. It is not just a circle, it's a 3D. Being 3D, it has three axes: x-axis, y-axis, z-axis. So this 0-ket, 1-ket are technically called basis state. Any system will have its basis state. So basis state is that it will rest into that's it will possibly it will have only these two states. But if it is excited, it will go to the cycle superposition. So like this, you can find out the basis state for almost all systems. But if you go to subatomic scale, and then if you want to mention them or if you want to represent them mathematically, we cannot use, see, in for digital we will use this kind of chart, right? This is 1, absence is the 0, 1, 0. You remember this clock cycle? 1, 0, 1, 0, 0, 0, 1, like this, right? But here in this kind of 2D cannot be used for representing qubit. That is the reason why we are using the 3D sphere, which is called Bloch sphere. Here, this Bloch sphere is helping you to represent the value in the represent the value of the spin of electron or polarity of photon with the cyclet. And the cyclet usually this is the value cos theta by 2 0-ket plus e iota sin theta by 2 1-ket. In another terms, it is also mentioned as, let me write it like this: alpha 0-ket plus beta 1-ket, which means the superposition has alpha probability of 0-ket, beta probability of 1-ket. Since it is a sphere, there is a formula like alpha square plus beta square actually it is root of alpha square beta square is always equal to 1, which is the modulus, r equal to that r operation magnitude, right? That operation is always 1. That's why these things are mathematically represented using unitary matrices. That is one reason we are limiting that it will be always within the sphere. So this is how qubits are mathematically represented. But if you want to understand physically how physically these qubits are built, that's what we are going to see next. Remember that this qubit is inside this quantum processor here. Okay, always remember that this quantum processor, which is at the end of the Chandelier approach, Chandelier structure, is having this kind of either electron or not photon. Mostly photon is used for quantum communication. It is not pure electron also. There are some things called Josephson junction in the superconducting structure that act as the qubit. Okay. Is this okay? Any question so far? So far, so good. Can you tell something about like pins which are they use for time travel in Avenger Endgame? The pins which are there. I don't remember that. Like pins which they are using. No, I don't remember that because the end game I watched only once. That the pins concept I'm not able to recall because the time travel and the pins I think these are all kind of fictional concept. Physically, it is not. Um, I don't think it is a physically available now. The people are researching on the time travel. But one thing I know about time travel is the time travel with the what is called. It is a kind of this kind of structure. This is present where the joining is a present. This is future. This is past. And if you are able to move the molecules or atoms to this direction, we can go to future. If we can come to down to past, something like that. It is mentioned in um, one of the mathematical lecture by MIT lecturer. Actually, if you search YouTube time mathematics for time traveling, you will see that lecture from MIT. So actually, they are discussing, but with the Avenger, with the context of Avenger movie, I don't know. Sorry about it. Okay, right. Let us move to the next topic, which is different ways to build qubits. Now, so far we are discussing these four, right? Yeah, sorry, here. Superconducting, trapped ion, photonics, neutral atom, annealing. These are all matured technologies to create qubits. But there are possibilities to use these technologies to build quantum qubits. Superconducting qubits, trapped ion, optical lattice, that is photonics based quantum computing. Quantum dot. See, the quantum dot is recently means I think 2022 February, Australia University, um, they built a quantum dot which will operate in the room temperature. Remember this image, which is a quantum process operating in 200 and minus 270 degree Celsius. But Australian University built a quantum dot for creating the qubit in the room temperature. But it has other technical change. Still, their research is going on. They are telling that near soon we will have a quantum computer which will work in the room temperature. Then it may be is we may be able to see quantum computers in the commercial use. As of now, the cost is huge because of that refrigeration unit. But the quantum dot is promising. You can build qubits in the room temperature. Coupled quantum wire, it is a nanotechnology based on the carbon nanowire method, where we can build qubit using the transistor. Then NMR, nuclear magnetic resonance. This is, remember the MRI scan, the medical MRI scan, which is used to scan the brain waves and then to find um, brain related disease. The same technology is used to build NMR. This NMR, I have a kind of experience, I can tell, meaning that experience mean not physically, I have not seen the computer, but there is a computer being sold by a company from China. I think the company name is uh, Sync, D-Sync or something. They are selling 2 qubit NMR devices, 2 qubit. If you are interested, let me know. I will share that URL of that organization, because if you search, the website will show some link that is not their company website. So because I have to check my email, because I received email from their sales representative, marketing people. Even they demonstrated the qubit, the quantum computer through video conference that will have only 2 qubit, that has a small display, LCD display. There only you can operate that. That cannot be connected to our monitor. It can be tested only through the LCD panel on the top of that one. It look like a Xerox machine only. The only condition is we should not place any magnet on top of that. That is the only condition they told. And also they gave me that when it is in operation, don't place any speaker or any magnetic material within 2 feet distance. That is the restriction while using that NMR quantum computer. But that is exclusively used for academic purpose only. We can't do any production work using that one. That costed around 8 lakhs plus excise duty. So I saw that NMR magnet, NMR quantum computer. That is very interesting one. Solid state NMR is somewhat improved version of this NMR. Then electrons and helium. This is also one of the um, techniques still under research. Then QED, cavity quantum electrodynamics, molecular magnet. See, the molecular magnet is a really amazing concept, because this year, 2023 March or April, they built one molecular motor using this technology, molecular magnet technology, which will have some 12 molecules, just 12 molecules used for build the motor, some movement device. So that is a starting point. So the molecular magnet is also one of the promising technology for building quantum devices, not quantum computing, quantum processor, but that can be used for quantum devices. And Fullerene, then linear optical quantum computer. This is, I think someone is exploring this one for building topological quantum computer, because linear optical structure can be put into lattices in the kind of tray kind of thing. After putting into lattices, the intersection of those lattices can be used for processing the information. Engineering, very difficult to engineer and then fabricate this kind of structure, but the research team is telling that this will allow you the topological based model. I'm not sure about the topological model, but that's what industry is climbing. Other promising one technology is diamond, and it is called NV center. This is very interesting concept, because diamond vacancy, it's really interesting to know. There is a concept called NV center. NV center inside a diamond. NV means nitrogen vacancy. See, we know that, center. We know that diamonds are made up of carbon atoms, right? It is full of carbons. Inside, while forming that, somewhere it is carbon and diamond mix. Somewhere else, the nitrogen may miss, or we can remove the nitrogen. So the nitrogen is vacant in that structure. So if you are able to form, create that kind of diamond, that can be used with optical technology to create qubit behavior. So what is qubit behavior? 0 ket, 1 ket, and superposition. So the nitrogen vacancy can be used for creating the superposition. Based on this approach, the industry is trying to build quantum computers using NV center in a diamond. That is very interesting. Initially, when I read it, it was very interesting, but I did not see any working quantum computer basing diamond. Then
Excuse me,
Bose,
KG.
Einstein. Yeah, yes.
There's question in the chat window.
Oh, Mayonara. Okay. Okay, Mayonara. Actually, it is not Majonara, it is Mayonara. It is called Mayonara. Mayonara, I have to recall that one. It long time back I studied about Mayonnaise. Give me a few seconds. I will, if I Google that, I will understand what is that one. Mayonnaise. It is called Mayonnaise fermions. Uh, so Mayonnaise fermion, a massless fermionic particle. I think I have to refer this, Anurag. I don't know exactly. I don't want to waste. Uh, but they are telling that this can be used for topological quantum computing. Certainly, I will explore this one and then come back. Sometime back, I read this one, Mayonnaise, but even that time also, I did not understand it clearly. I think it is beyond my knowledge level. But it is very interesting because that is promising topological quantum computer, which Microsoft is exploring to build. That I know. Microsoft is trying to build topological quantum computer using Mayonnaise fermions. That only I know. But how this Mayonnaise fermion is working, that to be honest, I studied, but I'm not able to understand. And anyone knows that one? If anyone knows, they can explain. Anurag, do you have any idea? If you know, you can explain because that will be useful. Okay, Anurag. We will learn together. We have a lot of list to learn together. Okay, right. Anyone in the team who knows Mayonnaise fermion? Because I myself don't know. I want to learn, but I am not able to understand when I read it sometime back. I studied it, then I left it because since it was topological quantum computer, I'm not comfortable because topological concept is also mathematically very difficult to understand. So I put it, okay, keep it as aside. Let us focus on superconducting quantum computer. Arul is typing something. Arul, do you know Mayonnaise? So they are particles that are their own antiparticles. Okay. Okay, thanks, Arul. That helps. Matter and antimatter, that combination. So, but how it is being used for building quantum computing, I think we will we will plan another session with more deep dive into physics. During that time, we will discuss. Okay, cool. Thanks, Arul. Appreciate your help. Then transistor-based quantum computer. Bose-Einstein condensate, that is one of the structure. And I'm not very clear about that one. Transistor-based quantum computer. See, you can connect this this transistor based with this quantum dot, because this transistor based quantum um, computer is using CMOS technology. You may recall that the CMOS technology is used to build our present classic microprocessor for digital computers, right? So this transistor based quantum computer is promising a room temperature quantum computer. Intel is researching on this transistor based quantum computer. Then rare earth metal ion doped inorganic crystal based quantum computer. The name itself clearly explains it's a rare earth metal. Uh, some of the newly identified uh, elements, those things can be used to build quantum computer, but this will use optical technology because of crystal nature of the crystal. Then metallic like carbon nanospheres. This is see, normally when we talk about that nanotechnology with the carbon, usually it will be a carbon nanowire, which is kind of string. But in this approach, they are trying to create nanospheres, then use that nanospheres as a qubit, but that's still in research phase, not fabricated yet. But you will be able to recall uh, the carbon wires can be used to create smaller transistors. This is the transistors structure, right? Carbon nanowires can be used for creating the transistor structure. But here they are trying to use nanospheres. Like this, to my knowledge, these are all various ways to build qubits, but scientific and engineering world so far is able to build quantum computers using these three technology only. Only these three technology. Other technologies are still in research, but there is no um, any feasible fabrication technique or technology is not um, devised yet. That is the reason why these other technologies are still in research stage. But if you keep on seeing the messages or observing the articles or papers in Nature or IEEE, those kind of things, you will come across a lot of new research is being proposed. So those things are promising that maybe in another 5 to 10 years, we will have commercial quantum computers which will sit on your desktop. That's what the industry is expecting. We are also praying for that one. Yeah, let us get a desktop quantum computers. Any other question? This is very interesting to know, right? So far, we know only 3 systems or 4 systems, but this much of possibilities are available. It is very interesting to know about the power of physics. Actually, physics can promise a lot of things. Quantum technology is one of the things what we are exploring. Actually, there is some use case. Recently, I come across when I talked to one of the expert. He is from in Bangalore only, but he is working on one of the hi-fi premier institute, research institute. It is not IISc, but it's attached to IISc. IISc had earlier had multiple organizations. It is spin out of IISc. They are exclusively working on materials and particles and those kind of things. There they are trying to find new materials. He told something that a new kind of material is being devised to build powerful aerospace system. Those things based on quantum technology. That's what he told. Also, there is one more thing for agriculture: quantum metrology or quantum sensing. Those devices can sense particle properties. Particle properties, as I told you, there's a subatomic level properties, right? Those particle properties can be sensed using quantum sensing sensors. We know, right? There is a sound sensor that will sense the sound. How it is sensing the sound? It is based on the sound wave, the sound wave vibration. The sound wave vibration is being sensed. This is molecule level. Even it is not atomic level. Similarly, light sensor, they are sensing the photons. This one is atomic level, and if you are able to detect single photon, that is subatomic scale. So quantum sensing devices are able to sense more subatomic scale particle properties. Those sensing devices can be used for building um, solutions for agriculture, health, military. So the quantum technology is growing in multiple directions in forensic phase. So we can hear information about the quantum technology frequently. So keep watching the news and then stay in communities where you can get lot of information. Okay, any questions so far? Cool. If no more questions, let us move on to the next topic. So these are all some of the images of those technology, whatever I have discussed. See, I have image for Mayanara, Anurag, Mayanara topological system. This is one, but as I told you, I don't know. Then neutral atoms, photonics, superconducting, trapped ion, and nuclear magnetic resonance, diamond NV center. These are all the images. related to those topics, whatever I have discussed. Okay. This PPT will be shared in your OneDrive, so you can download if necessary and use it. Yeah. Any question?
KG, there is question in the chat box.
Is it real, sir? Can you tell about Microsoft Azure? Is it real quantum computing? Arul, Microsoft Azure Quantum. I am thinking that you are asking about the Microsoft Azure Quantum. As of now or till date, Microsoft Azure Quantum is a simulator. It is not the real hardware, but they are promising that they are going to provide real QPU, quantum hardware access through their Azure cloud for IonQ. Then Microsoft itself, they are trying to build a topological quantum computer. That quantum computer, and they are also talking to an European-based organization to provide their quantum hardware. So the industry is expecting a news from Microsoft such that Microsoft Azure Quantum will be giving access to real quantum hardware in near future. Maybe end of this year, they may provide access to real quantum computer. Three things: one trapped ion, one topological quantum computer, other one is neutral atom or superconducting. That is based on the European agency. This is what I know about this Microsoft Azure Quantum. But I worked in Microsoft Azure Quantum simulators. They are good for optimization problems. Okay, hope that helps. Cool. Now coming back to the our discussion. So this comparison will help you how the industry is deciding which quantum computing technology to use. For example, superconducting loop, it is a resistance-free current oscillates back and forth around a circuit loop. An injected microwave signal excites the current into superposition states. But the longevity is only 0.0005. So some few are 5 or 50 nanoseconds. Success rate is 99. Trapped ion, it has greater than 1000, meaning that milliseconds. We can hold the superposition in milliseconds. That is one reason why industry is trying to build trapped ion systems. Quantum dots 0.03. Topological, it is not applicable for this one. Diamond vacancies 10. This is really cool. 10 seconds it can hold. Okay, so hope this comparison helps you to understand which technology is being used. This is microwave, this is laser. You can see laser is used for trapped ion and diamond vacancies, and microwave used in quantum dots and superconducting. Topological, as I told you, it is still the braided box can encode quantum information. I believe this comparison helps a lot. Okay, cool. Very nice. So this is the timeline of quantum computers. The timeline of quantum, see, initially it is quantum mechanics, then only we will see quantum computer. Obviously, that is the growth, right? Quantum computers are recently. So in the quantum mechanics, in 80s, in 1800, we had double slit experiment and discovery of electron, then black body radiation, Planck's constant, neutron, Dirac notation. This Dirac notation is very, the 0 ket, 1 ket, this peculiar representation of these things was introduced by Dirac. Dirac is the atomic research, what is called molecular atomic or research scientist, physicist. He found that every time drawing a vector like this, 0, this is for 1 ket. This is how actually the 0 ket means it is, this is a vector. This is what meaning of this 0 ket. So every time instead of writing like this, he wanted to find a shortcut notation. That's why he introduced kit. Similarly, there is one more concept called bra. This is zero bra. This is zero kit. Usually they will tell like this: kit zero, zero bra. That is how, or else kit something like that. They will. So what is the meaning of this one? If I put zero bra and one kit, it is the inner product of zero kit and one kit. They will conveniently represent like this. Actually, this is a mathematical representation. If you read this book, Michael and Nielsen and Chuang book, you can see these notations clearly mentioned. I am referring to this book. This book. If you read this book, in this book, I think in the page number 62, yeah, page number 62, they have, yeah, in this page here, they have mentioned about those notations. It is good to have this book and then refer this page number 62. That will help you to understand this kit notation. Why I am spending more time on kit notation? Because everywhere, any quantum computing literature, you will come across the kit notation. That's why you should be very comfortable. Then wave particle theory, then electron microscope, EPR paradox, Schrodinger cat. And most of you heard about the Schrodinger cat. That is the one way how or one popular paradox where the superposition is explained by Schrodinger using the paradox cat. Then quantum logic, then quantum tunneling, quantum field theory. Those things are introduced in 1940. The quantum tunneling is one thing where which caused the threshold of nanotechnology. Then NMR, MRI scan, then superconductivity, then quantum entanglement, quantum operators. These things have been uh, identified. Then quantum machine, large hadron collider, quantum teleportation. These are all quantum mechanics related inventions or discoveries. Now moving on to the next. Any question for anyone, or anyone want to share any concept here? The book name, I will type the book name. It is Quantum Computation, Quantum Computation and Quantum Information by Michael Nielsen and Chuang. Nielsen and Chuang. This is one of the important book. Also, there is one more book. It is called Quantum Theory in Graphics. This is very interesting book, very small book. I don't have that book now, but it's at home. So that book will give all the physics concept, the timeline, whatever we have discussed in a interesting cartoon-like story. There is a lot of images into that one. Even if I think that book is available in Amazon, I bought it from Amazon. So if anyone interested, please buy that book. That book will cost around some 475. But Nielsen and Chuang, it will cost around 900 in India. So you can buy these two books. It is really worth to spend a lot of time. Further, if you want to learn, I recommend these books. Dancing with Qubit by Robert Sutter. Then Quantum Computing for Everyone by Chris Bernhardt. These are all the good books. If you want to understand the quantum computing, both physics, mathematics concept, personally, I feel that you might have read all these four books. Any question? Okay, right, cool. Let us continue with the timeline. Now we are going to discuss quantum computers. So conjugate coding, no cloning theory, reversible gates. The reversible gates are one of the important discovery or one of the important concept which proved that mathematically we can process quantum information. Then superposition and quantum information theory. See, the quantum information theory is very interesting. You see the timeline is 1970 to 79. During that period itself, Richard Feynman talk about that one, but no one paid attention. So, but in 1981, I remember, yeah, 1981 or 86, he released the quantum information or quantum computation based on the quantum information theory. Both Richard Feynman and Chris Benoit, they released that one. That time also people did not pay much attention because the Turing machine also devised at the time, Toffoli gate, all those things were come. The universal quantum computer as a theoretical concept, like finite state automata, something like that. Then quantum annealing. These things have been introduced that period itself, but people did not believe that one. But in 1992, you see this Peter Shor's algorithm. You can see that is 1992. Exactly, it's 1992. In 1992, when Peter Shor introduced the algorithm that um, a quantum computer can break your security, your cryptography systems using factoring algorithm, then only the whole world wake up that and then paid attention to build quantum computer or research on quantum computer. So the Peter Shor algorithm, this is the one of the important event in quantum computing timeline, which created the interest and the necessity among scientists to build quantum computers. Is it clear? Then 1994, Groyer algorithm was introduced. Then quantum cryptography was introduced. Quantum dots. Remember, I told you the room temperature. Then superconducting circuits. All those things were introduced. See, the superconducting circuit were introduced in 1998 or 99 during that period. After that, IBM started research on. Maybe IBM might have started researching earlier, but after the superconducting circuits did, IBM built their quantum computer in 2007, if I'm not wrong. They built their 2007 itself. They built. Then 5-qubit NMR QC. See, NMR quantum computer is very easy to build. Remember, I told you I saw a quantum 2-qubit NMR quantum computer, which is a Xerox machine size. So usually it is very easy to build. The only challenge is that MRI scanning system that will be bulky, and being the powerful magnet, it has a lot of restriction to be placed in a normal commercial environment. It can be kept only in this specialized lab only. Then in 2010 to 20, very important inventions or discoveries have been done. SET. SET means single electron transistor. So one single electron started, they are able to fabricate transistor using single electron, one electron. Then quantum dot is improved during 2010 also. Then diamond quantum memory. See, this is very interesting, and this is one of the recent in discovery or invention. They are able to build quantum memory in diamond. Now, if you are following the quantum mathematics and all those things, now you will get confused. How it is possible to hold quantum information? That is really very difficult, right? Because quantum information, it is a superposition. The superposition is very fragile, and it is the coherence is very less time. The fidelity, they call it the fidelity, that is very less in terms of microseconds or nanoseconds. So how it is possible to build a memory, um, but still they started building that, and that is promising a technology for QRAM. If QRAM is built, most of the algorithms will start working. As of now, the industry is not able to build powerful processing algorithms because none of the quantum computers have memory. If you follow the industry, you can understand this one. There is no quantum memory. All are quantum processors only. There are no quantum memory. That is the reason why we are not able to use quantum computers the way how we are using our classical systems. But this diamond quantum memory is promising something. Hey, in near future, you can store the data in memory, then get it, process, then put it. If that is the case, the current approach or hybrid or variational quantum algorithms, they can be built using real or pure quantum algorithms, right? HHL. There are many quantum algorithms. They need quantum RAM memory. Even some of the machine learning, quantum machine learning algorithm, they need memory. So we are eagerly waiting for this diamond quantum memory to mature and being utilized, being part of any quantum computing, future quantum computer. Then these organization built quantum computers. Then IBM released their cloud, IBM Q experience, that was released in in the period of 20. If I'm not wrong, it is 2017. IBM introduced only for selected people, but 2019 they made it public. Yeah, 2019 they made it public. 2017 Microsoft introduced the language Q Sharp, but yeah, but that people are. I worked on Q Sharp. That is a language of different genre. If you see, it is very difficult, even very difficult to understand. But they have the very good language constructs for writing quantum algorithms. I believe that when Microsoft introduced the topological quantum computer with the Q Sharp, that will be a killer combination. We are waiting for that one. Then hot qubits, artificial atoms, then single photon source. See, this is single electron transistor and this is single photon source. These two things are very, very important concept. And quantum repeaters for building the longer quantum network. Synthetic molecular. Oh, I remember I told you there is a molecular magnet based that is called synthetic molecular motor. Then QKD, quantum key distribution. Then Quantinuum released their H12 AQT Pine. This quantum computer actually 19-inch rack system. If you remember 19-inch rack, this is the standard classical data center size. So the Alpine quantum technology are able to build a quantum computer which can fit into 19-inch rack. That is February 2023 news. Then India built their own quantum network in New Delhi, connecting NICNet to I don't know where they are connecting. It is a 40-kilometer or 48-kilometer network. So these are all happening. By seeing this one, we have the confidence that the industry is growing in a right path, and in near future we will have commercial solutions based on quantum technology. Any question here?
Yes, KG, in chat box there's a question.
Oh, okay. Sir, which is the most capable quantum computer in the world right now? Yeah, IBM is claiming that they have 433 qubit, but their quantum value is 128. But there is one more organization. They have recently, yeah, the Continuum H12. Yeah, remember this Continuum H12? The Continuum organization, they are telling that they have built 128 quantum volume qubit. So there is a Google Sycamore, they are claiming quantum supremacy, but recently I'm not seeing any news. Recently means for the past 3 months. I'm not seeing any news about Google, but Quantinuum and AQT Pine, they are claiming that we are building powerful quantum computers, but we have to wait. And Microsoft is claiming that we are building topological, but that also sometime like last year they first published a paper, then recalled a paper, something happening. But still, as of now, IBM has the highest qubit system, which is 433 qubit. And they are telling that in November 2023 they will release 1000 qubit system, and in 2030 they will release 1 lakh qubit system. That's they are climbing. We have to wait and see. And there is another question: and which quantum programming language is the most useful? I can't say most useful. I can say it is more popular. If you look into the software ecosystem, Qiskit is the most popular quantum computing language. It is based on Python. So almost all quantum computing framework or ecosystems are based on Python. So obviously, you should be strong in Python. After learning Python, you can import any one of these packages. See IBM Qiskit, AWS Bracket, Google Circ, and Xanadu Pennyline, D-Wave Ocean, Rigetti Pyquill. Yeah, these are all popular quantum programming ecosystem framework. All are based on Python. Q Sharp, entirely different language. It is not based on Python. That is where Microsoft standing out differently. Personally, I like Q Sharp. Mm, It was really very powerful construct I saw in the Q Sharp. Yeah. Now I think today I kept less concepts because I thought that I don't want to overload all of you. Okay. So now I open to question and answer. If you want, I can go back to the previous slides and then explain all those things.
Excuse me, KG.
Yeah. Yes.
Then shall we ask participants to on their video for a screenshot?
Yeah. Sure. Please switch on your videos cameras. We can take a screenshot. Nitish Gupta asked a question: topological qubit exist? Yes, Nitish. It is in research stage. The industries they are able to build um, topological qubits. Hi, Lingaraj. How are you? That's great. Nalini madam, you can stand sometime till you take a photo.
Uh, can I ask a small question
Yes,
while,
Vinesh.
I mean, am I audible?
Yeah, yeah. Yes, is it Lingaraj or Arul?
Okay.
Who?
Yeah, I'm Nitish.
Oh,
I
Nitish.
ask
Yeah, go
about
ahead,
topology.
Nitish. Yeah, yes, Nitish,
I have
please.
a
Yeah,
small question
Deepa,
like
take a photo. Yeah,
okay,
go ahead. Go ahead.
like topological qubit. You told that topological qubit is exist, but actually, I mean, theoretically it is exist, but I read some papers, but it they shows that I mean, in experimentally there is no topological qubit is right now. So I mean, it is true or not that?
Usually this kind of research they will keep secret only, right? Mostly with our network and then with more close people we will come to know that some organization is working on topological something like that only we will come to know. So there is no any published information about topological qubit, but there are, to my knowledge, because of my network and all those things, because we are closely with the people who are working on those things, right? We know that there are uh, at least to my knowledge, 4 organizations around the globe, they are working on the topological qubits.
And
Yeah,
one more
we
thing
can
is
shut
that
off the video cameras. Thank you. We can shut off cameras. Thank you. Yeah, yes, yes, Nitish.
uh, I'm on the like phone, so uh, but my next question is like about topological qubit is that as we have heard about that if we make the topological qubit and build the quantum computing by using topological qubit, then there will be no error uh, because it has some intrinsic property that can be, I mean, that is very and that can be make a very fast quantum computer or very, I mean, good way to build a quantum computer. So is it right that that's why
You
we are
see,
planning to make
yeah,
topological qubit?
you are seeing my screen, right? You see,
Yes.
there is no question about longevity or logic success rate. The point, whatever you are telling now, that clearly indicates that there is no longevity problem with the topological qubits. That is something like our classical systems, right? In classical system, we never had the doubt that how long your memory will be there. As long as there is a power, that will be retained. Even if you have hard disk, even without power, it will be retained, right? Something like that. Some the topological qubits are promising something like that longevity issue, no fidelity issue, no, and because of that, the success rate also high. All those things are there for topological qubits, but the problem is this kind of bride, the building these kind of brides, the brided path. It is engineering. It is how to say fabricating this kind of structure is one of the engineering challenge. The industry is still working on it.
Okay, and I have some more small question regarding this
Please.
quantum computing. Actually I just joined your talk, so I didn't know that you already answered or not. But actually, I'm like in India, there is a like future to any company who's building the quantum computer and going in a good way, like European or IBM or Google already made their quantum computer using something 200 or 300 qubits. But in India, I have not heard about that there is any computer which is made by 200 or 300 qubits. So, I mean, if you know these type of company,
Actually,
I mean,
to be honest, again, this is a kind of insider information. Uh, Only government organizations are researching into that building quantum or hardware, not private sectors. In private sector, uh, I can't say the name and all, but one of the topmost or one of the enterprise is trying to build quantum hardware in India. There is
okay,
one organization, I know it is a confirmed news, they are trying to build quantum computers. But government organizations like CDAC and then DRDO, they are experimenting with the quantum technologies, like for quantum communication, then single source photon or optical devices. Those things Indian government defense organization are researching. And CDAC is one of the premier organization working on those hardware related stuff. And even in Bangalore, RRI, IISc, they are also researching on hardware side.
and I mean, one more small question arising from my mind,
Yeah, yeah,
like.
please go ahead. No problem.
Okay, thanks. And the question is I'm a master student in doing the quantum computing, but the problem is that I mean to go with this path to go with the deep of quantum computing or researching is also challenging for today's, because still we don't know that this will be made in the future or not. I mean, some professors or some guidance always say that today's I mean in today's market there is a lots of hype that most of the student goes with the quantum computer, but we actually don't know that theoretically it is like we have many algorithms, shorts, grovers, and many. But I mean in actually setup we don't have, like we cannot apply shorts and grovers because of the error correction problem and many more problems. So I mean in the future it is right to go in the field that it is safe, that I'm confused always with these things, like quantum computing field.
Okay. How many of the attendees have this same doubt? Because I believe that um, when I when I discuss with multiple people, 60 to 70% of the members have the same question. KG, are you sure that the quantum computing is going to be a career? Is just a hype which is going to blow after 3 years or 4 years, after 10 years? No, 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 it is not possible. All the quantum computing experts go, go, go. You don't have job. That is very interesting. I heard this many times. See, to answer this question, there are three aspects. First one is what is happening actually in the industry, right? For your information, I'm following this industry since 2004. So nearly 20 years I'm following the industry, right? After following the industry since 2004, I moved into full-time quantum computing career last year. So nearly after
Okay.
18 years, I switched over to quantum computing as my career. I was in a corporate job, resigned, and then moved to quantum computing, full-time quantum computing career. This is first point, right? Second point, are you ready to spend your time in learning mathematics, physics, then programming? You have to learn
Yes.
these three things: mathematics, physics, programming. You have to learn these three things. Only then you will be able to survive in this industry. Most of the people are not ready to learn mathematics. So those
Uh,
who are ready to spend their time on mathematics, physics, and programming, they only can survive in the industry. That is the second point. Third point, There are many algorithms. There is a website called Quantum Algorithm Zoo. You search for Quantum Algorithm Zoo. I'm typing in the chat window. Quantum Algorithm Zoo. There is a website. In that website, you can see how many algorithms have been added. Sometime back, when I checked that algorithm zoo, they have only 22, 23 or 24 algorithms only. Now, if you check, you will see more than 47 or 70. Now it is growing, which means more algorithms are coming into the industry as a to build solutions, right? And apart from that, the timeline, that is one reason why I played the timeline. I showed the timeline. If you see the timeline, there are promising discoveries and inventions are happening in which are promising room temperature level quantum computer. The quantum computer will become successful only when we have a commercial system which will sit on your desktop or which will be easy to buy and then keep, right? The AQ2, Alpine Quantum Technology, they have built a quantum computer in 19-inch rack system. So the form factor is reduced. Only problem is temperature. That also will be solved. Something like this. There are many promising discoveries and inventions are happening. People are put forth a lot of efforts. So in 2025, 26 onwards, you will see demand for quantum computing professionals. See, for your information, recently I conducted a session on AWS bracket, right? When AWS bracket was introduced, it has only one simulator, one annealer, one quantum computer. Their own demand, their own simulator, then D-Waves annealer, Rigetti system. But now AWS is offering Harmony, IonQ, Rigetti, OQC, QEra. There are 5 quantum hardware available in AWS bracket now. Then think about. So it is real. It is become real. Quantum computers are become real. They are being used for building proof of concept as of now. Near future, those proof of concept will become real life problems. Arul, to answer your question, it is not strategy group. Any question? That's very interesting questions, Nitish, because whatever you ask, most of the members have the same question. Good that because of your question, I am able to answer those questions. Any other
Thanks.
question from anyone? Cool.
So first of all, I would like to know which part of quantum computing you work on, particularly whether hardware or algorithms part. And in your opinion, which is a better career path for quantum computing, to be in the hardware side or to be in algorithm side?
Okay. Hardware side is really a lucrative career if you are from physics background. If you have a strong physics, you are a doctor in physics, you should be a PhD in physics. Then I will recommend go to hardware. If you are from software side, you are a software engineer. My recommendation is, or at least this is what I follow. I am a software engineer and I become a data scientist, having 8 years, nearly 8 years of experience in data science. Because of data science knowledge, I am able to learn quantum machine learning. Through that quantum machine learning, I'm able to enter into the quantum computing career. Is it clear? This is what my path. So if you are a software engineer, my recommendation is that software engineering, data science, quantum machine learning. That is the kind of sure shot. Certainly you will get the career switch. Does it answer your question?
Yes, sir, I got it.
Yeah. But whatever it is, you should be a mathematician. Whether you studied physics or computer science or electronics or triple mechanical, whatever it is, you should be a mathematician. But if you have studied mathematics as your main subject, obviously you can learn anything. So mathematicians are first preferred skill set for quantum computing career. Unfortunately, we are seeing very less mathematicians, right, these days. Even if you see BSc mathematics, MSc mathematics, or PhD mathematics, the number of people are getting reduced. But it is unavoidable. If you are trying to pursue quantum computing career, in my opinion, you should have a strong mathematical knowledge, not just knowledge. You should have a passion towards mathematics. Okay. Any other
So
questions?
one more,
Yeah,
yes, sir,
please
one
go
more
ahead.
question regarding your domain, that is quantum machine learning. So
Mhm.
I am also a software engineer, and like we do machine learning tasks, many epochs are run in a deep learning model and so on. As we know in quantum computer, when we run an algorithm, we go for 1,000 shot or 2,000 shots. That is for one calculation. Now, when you run for multiple epochs, how do you like, how much training time do you take, and how does this thing work?
Usually, this is not pure quantum algorithm, right? It is a variational or hybrid algorithm. Am I right? What you are referring is,
Yeah.
yeah, it is not pure quantum. It is always hybrid only. So when you are building the hybrid algorithm, the each epoch result will come back to classical systems, then fine tune the parameters, then send back to quantum computer. That is how we are running. If you see any of the hybrid algorithm QML approaches, most of the QML approaches are hybrid, and every attempt they will come back to the classical, then go back. So each epoch it will come back to classical, then send the result. That is how we are executing now. Hope that answered your question.
Yes, sir. That is the only thing that we have achieved, or anything else in quantum machine learning?
In quantum machine learning, see, the industry is so far they have built quantum neural network, quantum support vector machine, quantum nearest neighbor, and there is some convolution neural network, and yeah, very few models, machine learning models have their quantum counterpart. But classical models have a lot of things, LSTM, BERT, and then LLM, chat GPTs. These are all various models available in classical machine learning. But all those things are not having corresponding QML, quantum machine learning model. So the industry has to mature, or it has to grow to have a corresponding quantum version of machine learning models. But there the problem is that quantum computers don't have memory. So any system expecting temporary memory cannot be implemented. So that is the reason why the quantum machine learning world is not able to reproduce all machine learning models. Only selected models are being here. That is the reason why we have to go back to, we have to follow hybrid approach. Every epoch, you have to go back, then store there, then come back, something like that. So it will take some time unless we have the memory, quantum memory, QRAM. It is not always feasible to build all classical machine learning counterpart in QML.
So, sir, as you are working on QML, are you getting like better results on QML than classical machine learning, or is it the same?
To be honest, even it is not same, it is less.
So, sir, like how is the QML industry surviving?
See, you understand one thing. Just as a hypothetical, I am telling you now. You are seeing AWS bracket now or IBM Qiskit now in 2023, right? Those people who built those things, do you think that they entered into the industry 2023? They might have
No.
entered the industry in 2010 itself, right? Those few people who entered that time are able to build services which we are consuming now. Am I right? Similarly, if you enter QML now, build POCs, toy problem, proof of concepts, theory, those things only you can work now. You can't build product now. That is the reality. We have to understand, accept it. I can't build a QML product in 2023. I can build only quantum inspired solutions which are running on classical HPC systems. Is it clear?
Yes.
So my take why I confidently enter into the QML industry. I will build algorithms, solutions, all those things now, which will be run when IBM or any other quantum hardware vendor is producing 1000 qubit system. That time only my algorithms will be commercialized or productionized. I am ready to wait for the next 2 to 3 years for the quantum computer to release 1000 qubit or 2000 quantum qubits will be released. That time, the algorithm what I built in 2023 operational in 2026. We have to wait. We can't um, build a commercial solution using QML in 2023. That is the reality of current status. Hope that answered your question.
Yes, sir. Got it.
Yeah, obviously for that you should be a lion-hearted person. Then only you can make such a how to say. But uh, you are seeing people like me, right? We are confidently entering and then surviving. We are able to build something. Um, you should be passionate about the subject. That is the one thing which we will be able to survive. Yeah, Shivam, do you have any questions, Shivam?
Sir, I have a doubt.
Yeah. Yes,
Sir,
please. Yes.
I'm an MSc graduate student. So if I want to follow a career in quantum hardwares, how would I actually get into that experimental or hardware part? What would be a better way to choose that path?
Okay, Arul, I know few of my contact in my network, quantum computing network. They are passionate about the quantum hardware. I will connect you with them. So two of them are in US, few of them in India. There are they are very much interested into quantum hardware. Say one person um, really made a lot of good things into that one. So you should be able to. I believe that you are MSc Physics, correct?
Yes, sir. Complete.
Yeah. So to be honest, in India, quantum hardware in private sector very less. You should be ready to relocate to Europe or US, where you can get a good opportunity. That is the reality. But you can learn those things here. I will connect you with the right people. They will help you to pursue quantum hardware related career. So ping me in our MyQT community. You are part of MyQT community, right?
No, sir.
Oh, okay. Then you okay. You can get the detail. Okay, I am typing the MyQT invite here. Deepa, can you paste the MyQT WhatsApp group invite? So Deepa will
Sure.
share the invite. You join that one. From there, we will be able to network with a lot of people who are in the industry. I am telling you, hardware people very less, but I have the correct contact who can help you.
Okay, sir. Thank you. One more question.
Yeah, go ahead.
Sir, in order to do the complex tasks, like for example, uh, factorization of large prime numbers, what would be the current capability of a quantum computer to factorize a prime number? What will be the highest capability, or what would be the highest complex task a quantum computer can perform as of now?
See, there are many premium services offered by IBM and these other hardware services. They are able to solve really very complex problems, a kind of near-term business problems. Exact statistics I don't know, so I don't want to give you wrong information, but you can believe me that uh, even 512 qubit RSA code can be broken.
Okay, sir. Thank you.
I think maybe that will 4 months or 6 months period. Cool. Navin, for you, please keep in touch with me, and then I can connect you with the right person who is into the business part of this one. In quantum technology, you have to go specifically whether it is a hardware or software. If you desired software, whether it is quantum finance, quantum chemistry, quantum machine learning, or any other quantum verticals like that, you have to identify that one. Then you can plan your business. As of now, consultancy training are the good business. At least you will be able to survive. So that is to my knowledge. Training is the first starting, because that is where you will find customers to survive your business. Hope that helps, Naveen. Very good. We have 4 more minutes. Those who are not part of our MyQT WhatsApp group, please join there, because we will next week and all, we are inviting industry experts to deliver more industry specific discussions. We are also planning to start our educational tour maybe in the month of August or September, a 5 days tour to Wayanad, where those interested people will come on leave. They have to come for 3 or 5 days stay at Wayanad. Then we will discuss and then learn quantum computing, only quantum computing, those 5 days. Hard, how to say, full focus without any distraction, we will learn. So those who are interested, they can register for the education tour. That will be September, end of August or first week of September. Like that, we are doing all, and then you all of you know that we have interest group. QML interest group is working on classical model now. From August 15th, they will start working on the quantum support vector machine. Next interest group on QML will be start on October. So like this, there are activities are planned for those who wants to pursue quantum computing career. It's great to see the momentum and a lot of new faces joining our team. And Lingaraj, I know Lingaraj is a hardcore physics person. And then, yeah, it's good to see many people. Thanks, team. Appreciate your efforts and then joining on a Saturday evening time. That shows that you are passionate about the technology. Thank you. Over to you, Deepa.
Okay, thanks, KG. Now I invite Lingraj for vote of thanks.
So where can I find the voting section? Hello.
Yes.
I cannot see any link for the voting section for the voting.
You can just deliver a few words.
Okay, yeah, in the link that you have sent me in the WhatsApp, right?
No, here itself, you can talk it out.
Uh, I don't have anything special to talk now. But the talk was really very nice. I enjoyed the talk.
Okay.
Yeah.
Thanks, Singlaraj.
Yeah. And
Ayan, yeah, go ahead.
I have few questions regarding the scaling of the quantum computer. So till now, like you have told, like it's around 400 qubits, right?
433.
Yeah, 433. So it's in the US, right? IBM.
Correct.
Okay, okay. So they are building with the superconducting qubits or different one?
Superconducting. That is superconducting. Yeah.
Yeah, so I have heard like this superconducting qubit and this trapped ion qubit. These two are the more popular at the current, I mean, at the moment, right?
Correct, correct. You're right.
Yeah, but like I have also worked with the NV center qubit. So it seems like the NV center qubit is also growing very fast because they can operate in the room temperature.
Hmm. Hmm.
Yeah. But the main problem everyone is facing that like the decoherence is the biggest problem everybody is facing.
Hmm. Yeah, that's true.
Yeah.
Great.
So is there any growth in any other qubits? Like as of now, we know that hyperthermal qubit and ultra fine qubit, these two are the more popular, right? So is there any advance, like any growth on any other qubit, like diamond qubits or maybe electron qubits or any other qubits?
Lingaraj, in the interest of time, I'm not able to take up this question now. Actually, in the
Okay.
next session, we will discuss, because next session, Aniruddha is delivering a session. During that time,
Oh,
we
okay,
will have
okay,
time. Yeah, that time we will
okay,
discuss this. Okay,
okay. Thank you.
cool. Thank
Bye.
you. Thanks, team. Appreciate
Okay,
your help. Thank you. Bye bye.
KG, thank you,
Yeah,
and thanks for all the participants for joining us for this wonderful section, and the time you have kept apart for joining us and encouraging us. Thank you, each one of you. Then a small information, there's a link sent in the chat box. You can give us your valuable feedbacks for the betterment for our next sections. Thank you very much.
thank you. Bye bye.